today, we're very pleased to have one of our own, Travis Glick, come back to present work on his master thesis, I believe. And Travis is currently a Ph.D. student in the civil engineering program. And for today, he will present on a case study of utilizing high-resolution transit data. With that, I will give the floor to Travis.
Thank you. He said, my research is a growing process, and right now I'm looking at high-resolution data from TriMet to conduct before and after studies. And this is a slightly less nerve-wracking version of my thesis defense that I did this summer. And I'm going to be showing you the methodology and then 3 case studies where the methodology was applied to explain how this type of approach can be expanded to other areas, different types of road diets, other road segments, different detours, and is generally broadly applicable. So first, my name is Travis Bradley Glick. I'm from Chico, California, which is a town of 100,000 people in the Central Valley of California. I have been at PSU since 2010, did my undergrad here, master's here, and all the while with Miguel Figliozzi as my advisor. December 2015, as a junior in an undergrad, he gave me a position at the Transportation and Technology and People Laboratory, and work has grown from there. Many publications, including this one, which was accepted yesterday and will be presented at the Transportation Research Board. So let's begin. Why? Why quantify roadway changes? What is the importance of knowing how something affected it? And really, it's about planning. If you know how a particular event influenced how a roadway works, you can make a good guess as to how that's going to affect something like it in the future, or be able to test something else that you do. If you implement a new change that hasn't been done, by quantifying it, you can know, well, was that a good idea? Was it worth the money? Should we do it again? For my 2 case studies, or 2 of the 3, they're road diets. And I'll get into what road diets are more specifically later, especially for these. But with transit, and I'm using transit data, it's understudied. Road diets are well studied in themselves about safety, pedestrian impact, how cars behave, do they slow down, travel speeds, but not buses. Buses often operate on these and they just kind of go, yep, the bus is still running. But by using actual transit data, we can see how did that change impact transit, and using the bus as a probe, also evaluate the roadway for other vehicles. So I'm using data from TriMet. I'm using stop level, disturbance, and high resolution data, which I'll explain the details of in a moment. But I'm also using GIS data from Portland Metro. They have amazing archives of GIS files to get a good idea of the city as a whole. Transit lines, where are they? Where do they overlap? I used RStudio and the R programming language to do most of the analysis, Excel pivot tables extensively, and then finally ArcMap. So stop level data. Stop level data is pretty much everywhere. Most transit agencies have a version of it to some degree. It is what happens at individual bus stops. How many people get on? How many people get off? Was the lift used? Did you need to dwell there long to get back on schedule? When were you supposed to arrive versus when did you actually arrive? And this information is very useful. It can tell you a great deal about stops themselves, segments, routes, even networks, and that's very useful. It has one pretty notable flaw, though, and that is it requires averages between the stops. And so if you have a bus that says it went 30 miles an hour between this stop and this stop, you don't know whether that means 60 miles an hour for half the time and stopped the other half versus an average. Problematic. I mean, yes, you can say, okay, well, the bus is getting there on time, but what's happening? Excuse me. But the disturbance data fixes that to a degree. It at least records information every time the wheels of the bus stop. So this adds in intersections, certain times crosswalks, general congestion. So it will record a bus stop and then it will record another stop and note it, disturbance stop, 3 seconds, disturbance stop, a minute and a half. By integrating those two, we again know what's happening at stops and averages in between those, but was your bus moving at 15 miles an hour between there, or at 10 for half and 20 for half? You don't know. And that's where high-resolution data comes in. So this data is recorded every 5 seconds along a route. As buses travel, they're dropping a GPS coordinate and a timestamp, every bus. And this is while the wheels are moving. And while there are only 3 here, note the data I was using had thousands. And so from this, we can get a lot of information. Pick one point, say 75 feet along a route. You know because of the GPS coordinates where these are and which buses. So you pick one point from the bus before that and one point after and calculate speeds. From that, you have a lot of information about what happened right there. An average, a median, percentiles by time of day. And then you can repeat this process along the entire route. And then from that, create profiles, however you feel. And by doing that, you can actually take more information, because I said before that disturbance data and stop level data are when the bus stops. Well, high-resolution data doesn't record if the wheels of the bus aren't moving. So it can have gone 4 seconds, but the wheels stop. It won't record again until the next time that 5-second marker has moved beyond the 4-second point, or the 5-second point. And so by integrating the data sets using date, time, bus number, route number, direction, you get a much cleaner idea of what's going on throughout the route. And this combined set is what I'm using to extract the information about routes. The GIS data was used as a really useful cleaning tool because the data is messy. Buses, when they're just stop level data, they'll record their stops, but sometimes they'll record extra stops, or they'll break down and still record, and you'll have a stop that's 3 hours long. It's not a good approximation of what's going on in the route. When they're off, and the high-resolution data says, well, this bus is actually in Montana, you know something's wrong, and you're able to fix it. And so I can use the information from the route, cumulative distance along that route, to accurately say, is the bus where it is when it says it is? And then clean out everything else, which includes a lot of times where they'll say, well, I'm on Route 9, click it on, but they're still on Highway 84 getting there. And so you'll have Highway 84 in your analysis. And so it's a useful way of cleaning data. So for this study, I decided to use 25 feet increments. And it was somewhat arbitrary, but it's shorter than the shortest distance between cumulative 5-second data. And then I extracted speeds before and after each of those points, and then compiled them in 2 different ways. The first is by percentile. So by percentile, you have the 95th percentile travel speed on top, which is going to be faster, and the 5th percentile travel speed on bottom. And these travel speeds give you an idea of what percentage of buses are experiencing certain behaviors. So in this case, to the right of the graph, you'll see 3 peaks. Those 3 peaks are bus stops. And you would expect the bus to be stopping most of the time for all of those. But then here, you wouldn't expect a quarter of all buses to be moving 5 to 10 miles per hour. But they are. And noting that it's that many is important, but then also noting when it is. And in this case, this is Powell Boulevard, and you're looking at the morning and evening commute. And while there is congestion definitely in the morning, it's less so in the evening, but still present. So this is the before case, before any changes went in. You then do the whole same process using data collected after and subtract them. And that gives you the graphs on the right, which are the differences in travel speeds at each point by percentile and by time of day. And I'll get into the details of the results a little bit later, but these are the types of graphs that you will see. The next type of graph is speed variability. This is really useful. It doesn't tell you exactly what's happening, but it gives you an idea of the range of actions that's going on a route. The 85th percentile is generally understood to be a free flow speed. The 15th percentile is a normal level of congestion or what you'll experience when things slow down. And so 85th minus the 15th gives you this graph. And it gives you information about what is the difference between those. So if you have a very high 85th and a reasonably high 15th, it's the same as a high 85th and a low 15th that are the same distance apart. It doesn't tell you exactly what's happening, just that there is a difference between those. You can then further index that by the 50th percentile. So a high value minus a low value divided by a high value is a number very close to 0. If it's above 1, it indicates that the 50th percentile is behaving more similarly to the 15th than to the 85th, and that it might indicate something is going weird. The 3 spikes on the right are bus stops, which again, you would expect. But you'll notice that the before and after, there's a much higher variability index before than there is after. You might have noticed on this past graph that the line thickness also is not uniform. And it changes, and that is the 95th percentile confidence interval of each of these calculations. Throughout this whole process, there's uncertainty, there's error. You have a certain number of buses, they are a sample of what you're examining. You calculate the 85th percentile, but it's really 85th plus or minus a range, the 15th plus or minus a range. Well, if you can assume that they're normally distributed, if you can assume that they're independent, you can add those uncertainties. And if you had 10 plus or minus 1 and 20 plus or minus 1, the end result is not going to be 30 plus or minus 2, but 30 plus or minus the square root of 2. And so that gives us the ability to know the range of likely values. If anyone has questions about this, ask at the end, because they're not independent, which complicates the issue. So let's get into the case studies. The methodology I described is just broadly applicable. And the first 2 I did were road diets, where they're projects that don't change the physical geometry of the road. The sidewalks stay where they are, the center medians stay where they are, but the lane striping changes. And by changing the lane striping, you can change travel behavior. You might take away a parking lane and add bike lanes, reduce lane widths to reduce travel speeds, change the lane markings to encourage certain behaviors. They have been shown to reduce travel speeds, and they have been shown to increase safety. But again, not for transit specifically. So there were 2 road diets in Portland that we had before and after data. The first was in North Portland on Lombard Street, and the second was right by the Lloyd Center on 15th and 16th. It's a swoop that changes as you go through. For Lombard Street, they ended up adding bike lanes and a center turn lane. If you look at the before case, you'll see there's just one dashed line all the way down. And then big wide lanes. This whole thing is 50 feet wide, so the travel lane feels like 15 feet, which encourages certain behaviors. In the after case, they decided instead to remove parking altogether, add the center turn lane, and reduce widths. Now this was really important because there's a new seasons right there, and so the turning volumes would have likely interfered. But again, this type of project can be done fairly easily. It doesn't require the traditional level of bureaucratic oversight because it's just repainting. You don't need to check that all of your sidewalks are right because lines get repainted all the time. Again, looking at the comparison, they have a very different feel. But for buses, not much going on. This is the difference between the travel profile before and the travel profile after. Basically, it didn't change. And so all the speeds are within plus or minus about 5 miles an hour across the entire segment, including the road diet itself. And the same is true in the other direction. And this indicates that, at least for transit, it didn't experience any increased congestion by lane narrowing, and nor did it really feel any decrease. For 16th Street, it was a slightly different project. They already had 2 lanes in each direction. They had a bike lane. And so if you look at the before case, the 2 lanes aren't that wide. there is a bike lane, and this is serving its purpose, but the traffic volumes are very low. And because they're so low, you don't need that many lanes. And so what they instead chose to do was remove one travel lane, take the bike lane from 5 feet to 8 feet, add a 5-foot buffer, and give a slightly wider travel lane. Now, this would be more interesting to buses, because in this case, buses are now definitely in the same lane as all the rest of traffic, rather than being to the right. But even with this change, almost nothing happened, with one exception. In the other direction, there was a new bus stop where they moved it, and for buses, they started experiencing congestion. So I went out, and I decided to look to see, well, is this bus now going to cause congestion for the rest of traffic? The answer to that is no. And it's because the bike lane and the buffer are wide enough that the bus is pulling fully into that lane, and normal traffic just keeps going at standard speed. So in both of these two test cases, which were pretty cut-dry road diets, low traffic volumes, no real question of whether they would work, for transit, seems to have no real effect, except for the added stop, which is to be expected. This methodology applied to these different types shows that it can be applied to other situations, larger road diets in the future, and be able to examine how things change for both transit and normal traffic. But this methodology was also applied to a very different kind of project, and it was the effect of the Tilikum crossing. The Tilikum crossing, for those of you who do not know, is a personal vehicle and freight-free bridge that crosses the Willamette River and carries the Max Orange Line streetcar, buses, bikes, and pedestrians. It's a very useful bridge and moved several different routes off of the Ross Island Bridge onto this new bridge. And so we wanted to look at what happened over that change from the before to after case, and then also look at it as it compares to the rest of the route. First, I'm going to look at just the segment immediately eastbound, where the two routes have merged from the before and after case. So up top is where the route travels now, and below is where it used to travel. We're going to start by looking just where they merged again and see, did it feel anything? Now, traffic volume stayed very similar throughout this process. In short, very little change except a new bus stop. The bus is now turning left at that intersection and could not be at the bus stop it used to be, so they moved it. So for buses, they are feeling that. And for the rest of traffic, again, very little change. But there's one thing, and that is this graph only goes to the 5th through 95th percentile. And so if you look at the lowest speeds and do it by time of day, some buses, a few percentage of buses, saw a notable decrease in their travel speeds during the commute from Portland out to Gresham over this segment. No change in the morning, but a few percent of buses did slow down. The other way is a very different story, and that 15% of buses saw increases of 5, 10, and even 20 miles per hour over this segment for the majority of the day, using 1,000 buses over the course of a month to calculate this. By time of day, this is almost all concentrated in the evening commute. So where buses used to be getting really clogged up as they tried to go from Gresham over this segment into Portland during the evening, they're now traveling much more smoothly. Now, is that a direct effect of the bridge? It's really hard to say. But it is a way to show that this methodology can explain, even on very high traffic streets, what the buses are experiencing. And as a note, there were no geometry changes to the roadway for this entire segment that you're looking at right here, with the exception of they repainted the lines exactly as they were. Looking back, this is the difference between the speed difference and speed variability and speed variability index. Since both of those values are greater than 1, if it's negative, it means that it's closer to 0. Now, than it was, and if it's positive, it's further from 0. And in both cases, it shows that the 85th and 15th percentile are more similar than they were. Now, that either means that one came down or the other came up. But what it does show is now consistency, that both of these, or this segment, is going to be more consistent because the speeds are closer. And for planning agencies, that's really important, transit agencies. And so looking now instead, not at a segment, but over where it changed, you can't do the graph I just showed you, because you can't compare individual points along a changed route. But you can compare travel times. And so looking at the westbound travel times all day, well, the travel times increased for most of the buses traveling over this. But note that the before case has a lower first percentile and a higher 99th percentile, meaning that the range of possible values throughout the day was much higher than it used to be, even though the travel time has increased. During the AM peak, it's basically the same story. Again, the width of the line is the 95th percentile. If you're only using buses from the AM peak, you have less data, more uncertainty. But during the PM peak, it's a little bit of a different story. That while most still experienced an increase in travel time, the highest 10% did see a reduction. And again, the overall range of values that could be experienced during that PM peak was sharply reduced. And this is wonderful if you're trying to plan. Yeah, it may take 10 minutes longer to get there, well, 4 in this case, but you can predict it. You know when you need another bus, you know when you won't need another bus, far more consistently. In the other direction, yeah, most increased, but even all day, the highest 15% saw a sharp reduction in their travel times. During the AM peak was not when that was happening for eastbound travel. So people traveling out of Portland during the AM consistently will see 4 minutes of increase. However, when you look at the PM peak and trying to get out of the city during the evening rush, 70% of trips saw a reduction in travel time. And again, the range of possible travel times is only a few minutes versus what looks to be close to 30. Expanding this to the segment from 205 to the bridge to see, does that change really relate to the rest? The answer is, again, yes, because the travel times did increase, except for those last trips. Those slowest trips in the before case are now more consistent than they used to be. And again, this is confirmed for that by time of day. In this graph, red is higher, blue is lower. In the after cases, you'll note that at pretty much all times of day, the difference in time is, or it's a higher travel time than it was in the before case. However, the deviation, blue lower, red higher, is much more consistent across all times. You don't have that 19-minute difference that is possible during certain peak travel. Meanwhile, passenger loads stayed mostly the same, even increased during some times, without much difference in the actual schedule. So for the Tilikum crossing, using this methodology, you can show that travel times increased, but that the range of travel times was sharply reduced. And this increases on-time performance, the ability to plan, and overall will reduce costs. And that is a main goal when you're trying to run a transit network, is you want to make sure that costs are low and you're getting to where you say you're going to be when you say you're going to be there. And by being able to predict that the buses are going to get there at this time is really useful. I mean, a 25-minute range or a 30-minute range of values within 2 hours, and any particular day could have a major difference in those values, is difficult to predict. So that's what was happening as buses tried to get from Portland to the east side during the evening peak. They might get there in 5 minutes, but they also could take 30. And if you're waiting on the other side for that bus, you're not going to be pleased. But instead, if you say, well, it's going to take 12 minutes, but it's only going to take 12 minutes, maybe a minute more, you're much more likely to wait for that next bus. So the conclusion of what I was trying to show was a methodology. And I used 3 case studies to show that it is broadly applicable. Different types of road diets, streets with very high traffic volumes, route detours, long segments. And because of the broad applicability, this could be used to quantify changes of many different types of infrastructure changes in the future. And that is what I hope it will be used for. I would like to thank all of these wonderful groups for providing me support for my research. I was a recipient of the Eisenhower Fellowship for the past year. NITSE continually helps. Miguel Figliozzi's Transportation Technology and People Laboratory provided ongoing support, as did Portland State and TriMet. Any questions?
For those registered students, please announce your name so I can record your question.
Okay. Will Gust. I noticed that you use RStudio to plot most of your graphs and all your statistical data. Just out of curiosity, how many data frames did you have to build to complete all this research? Just ballpark figure.
Took a good processor. There were times I was using 40 gigabytes of active RAM. It was just a lot of data trying to get it down to what I needed. Most of what I did was get it to a point where I can extract what I need. So I used one big file that had everything. And then I would take everything I needed with simple algorithms and then do the actual analysis just on small segments. Otherwise, it would take forever.
My name is Lorena. Could you go back to the number of passengers, because I was curious about that? And yeah, so it increased, because I take the 19 bus, and I go to the Royal Island. And during peak hours, we spend sometimes 30 minutes, 20 minutes, just going through PSU to cross the Royal Island. And once it goes, take the other bridge, I don't know if we'll read this, so I was curious about that. Did it increase or decrease?
The passenger loading?
Yeah.
It stayed relatively similar. It decreased for some hours, decreased for others, but in...
During peak hours, did it decrease?
Let's take a look. During peak 5 o'clock, it stayed basically the same. On average, it didn't really change. Now, this is preliminary for passenger loading. This hasn't had time to really sink in with Portland what the change was.
And sometimes you were used to take the same bus stop and then go.
Yeah, 3 routes, I believe, were diverted from the Ross Island to the Tilikum crossing. It was somewhat expected that travel times would increase, but again, this is about consistency. So even though most trips are probably going to take longer, it's the range of possibilities. You're not going to have that weird variation of being unable to know.
Thank you.
Santiago. So the travel time increased because of the distance is longer, or there's an extra bus stop? Is there very specific?
So over the bridge, there is a reason. The Ross Island has a speed limit of 45 miles per hour. Cars don't go 45, they go 55 as a pretty standard rule. On the Tilikum, the buses go 25 or less, and it has to do with sight lines. When you were on that bridge, they had to make sure that the Portland Spirit could go under it, and so it has to go up a very long way and down a very long way. And because of this, there are terrible sight lines for the bus, the trains, and so they made the speed limit only 25 miles per hour. And that's a long bridge. So it means that the lead up to that is slower because it's on tracks, and then the bridge itself is slower. And even though they're almost exactly the same distance in terms of route length, if you have the speed, for most of it, it's going to increase travel times, even in the best case.
Hey, Travis, thanks for the presentation. My name's Luke, and I'm with the Portland Bus Lane Project, and we're focused on helping increase bus speed and reliability across the city. I had a question. We're thinking about doing a pop-up bus lane on Southwest Madison approaching the Hawthorne Bridge. If we were to do that for a week, do you think there would be enough data there to show whether there had been a decrease in travel time, increase in reliability. Both in that segment, it was interesting looking out the Tilikum crossing further out across the routes.
So on heavy routes, if you don't count weekends, because they do have different behaviors, you get about 1,000 buses every 3 weeks. You need a large sample size for this type of analysis. It kind of loses effectiveness below 160. In fact, the previous research says don't do this type of statistics with low counts. And so I would suggest having as many buses as you possibly can. It does depend on the number of routes. So one route might get you this much, but if you can get to that 400-ish bus range, you can at least do all day pretty well. But you're going to need to increase that a lot in order to be able to look, well, did it help it in the peak hour? And so it depends on number of routes, it depends on a lot of different factors, and it depends on whether you have the data before. All of this data, all of the high-resolution data is on a rotating schedule at TriMet. They delete it every 3 months. It's enormous, and otherwise they would really need new servers every couple of months. So they rotate it through. So a project like that, you would request data, implement it, hopefully for long enough that you would get enough information, and then request data again for that period.
Yeah, and just I'm making an extrapolation. Tell me if I'm right or wrong, perhaps. In the road diet part, in the road diets, you take out one part of the roads to make the turn, right? If we think of instead of doing this turn, right or left in the road diet, you would take one lane and give it to the bus instead of that. Do you think the results for cars would be the same?
It's an interesting question. It has been done. Road diets that reduce a lane and give it to buses have definitely been done, mostly in cities where you need the bus to not get trapped in grid traffic. For cars, I don't know. Part of the best benefit of road diets is their safety for pedestrians. If the pedestrians only need to cross 2 lanes rather than 4, or even 3 lanes rather than 4, that is safer for them. And in that case, for pedestrians, which wasn't exactly your question, they'd still be crossing a bus lane and a travel lane. And do you put them on both sides? Do you get rid of parking? Does the area need that? And again, it depends. In road diets, there's a lot of variation. And how you implement them is very dependent on, well, what situation you need. On Lombard, they needed the center turn lane because there's a new big market. Being able to remove or add a big buffer on 16th worked because, well, it has low traffic volumes and you don't really need 2 lanes. So it really depends. If you're up to 20,000 people per day and you take away a lane and add a bus lane, probably will cause problems. But it's hard to know.
So with that lane diet, I was wondering how much does the bicycle lane in itself determine whether the reduction should happen or not?
So one thing to note, I'm not studying road diets specifically. Whether to put in a bike lane is a question that a lot of road diets look at. Can you remove a parking lane to do that? Can you remove a driving lane to do it? It depends. So the actual decision of if you put one in, which I'm not sure if that's your question.
We don't need this lane, or because other things have more necessarily.
Well, there's a big crosswalk on that street across 16th, right at the center. And it's Lloyd Center traveling to homes. It would make sense from the literature, although I do not know if this played into this location at all, that reducing the number of travel lanes that the pedestrians have to cross made sense. And bike buffers have regularly been proven to be safer than normal bike lanes. And the bike lane was only 5 feet for a pretty high traffic area with bikes. Making it 8 with a 5-foot buffer is safer for bikes, it's safer for pedestrians. So in this location, that would make sense. But again, I don't know if that was the reason behind it.
And I don't mean to keep talking about road diets, but I travel on Williams to work on my bike. And it's very common for the TriMet bus just to sometimes stop almost completely in mid-lane. Or if it does pull over, so my concern is that you're saying, well, the bus can easily just slide over into the bike lane, which means the cyclists are now trying to get, either I stop and wait for the bus, or I go around, and now I'm risking being out in traffic where they're not expecting to see me. So is anything about that being addressed?
Addressed with my research, no. There are many studies regarding that specific issue because it's a big issue. Happens almost everywhere there's a bike lane and buses with one lane. They pull into the lane and the bikes either have to stop, get in traffic, go on the sidewalk. There are design solutions where you weave the sidewalk in the bike lane, or you put the bike lane on the other side of the sidewalk. But those type of things are not road diets. They're very expensive. They require full oversight of ADA and consideration of buildings, traffic impact analysis. When just restriping, while not perfect, as in maybe it gives you a buffer, the bus still pulls in, it's better and significantly cheaper, even if it's not great. Even if it wouldn't be the best solution in that area, it would be better than the status quo.
Much of the response is through driver training, actually. That's why I think in Portland it's much better than in other cities. Through driver training and not design or engineering.
I'm curious about the segment length that you were studying. And I'm curious if there's opportunity, whether you or someone else, for future research, perhaps with a longer segment, and if that would be, if you could extrapolate similar data results by maybe using, I know you said you were using like every, was it 25 feet?
Well,
if you expanded that, it sounds like all of the data is really bulky. So I'm just curious if you think you would get any different results, being that on Lombard and 16th there wasn't much change to be reported.
So I've done that. I've tested different distances, and one of the reasons I picked 25 is because it looks very clean. You don't get a lot of extra information above that resolution because the distance between consecutive GPS points is closer to 200 feet. Now, as you move forward, you might switch a bus, or 2, or 10, or 20 that move to the next set of paired points. You get more, but not a tremendous amount more. Now, that is going to change very soon. TriMet is working to implement 1-second resolution data, which means that the distance between consecutive points is going to be less than this value, in which case you're going to actually miss whole segments that the bus was traveling, and you don't get as complete a picture. So it depends on the resolution. If you're using 30-second high-resolution data available in certain cities, a larger distance won't make any real difference. I chose this because it was less than the 99th percentile shortest distance between consecutive points. But I've done it at 50. I've done it at 100. I've seen it confirmed other ways, where you extrapolate points up to areas. So you take those and then calculate artificial points at barriers. Whether that's 50, 100, 25, you get similar results. But then visual resolution does matter. If you're using a very long distance and you go a little longer, you're going to gain good information. But if you get up to, say, 200 feet and your bus stops are only 600 feet wide, you're not getting as much if you want to know how that intersection affected it.
The consecutive GPS points which you are getting in high-resolution data, are you considering the likely to be average? And if yes, how are you addressing the variability in them?
So in most of what I'm doing, I didn't look at averages at all. I have in the past and used the harmonic mean to calculate these types of speed averages. But in this, I'm using percentiles. And so I am ordering all of the data. And if I want the 85th percentile, I'll pick a speed 85% of the way down the list. And then I am using probability theory of statistics to find confidence intervals based on that data. So I'm not, in this research, I'm not using averages at all.
Okay, then what if the value meant before, what about the dependence assumption, right? So I will assume that segments with tall buildings or segments with trees probably have a higher disturbance than those more in the open. How do you address that?
If you take the 85th percentile of a data set and use the same data set to calculate the 15th percentile, even a range, they're going to be correlated to some degree. And so to do that, you add in covariance into the propagation of error. You relate how related a distribution of random sampling would be. If you're doing that random sampling, the data doesn't always look like what you would want it to. This is real data from what I was doing. That's real data. That's real data. That's real data. The one at the top is real data. You get all sorts. You get bimodal, trimodal, things that look like Poisson distributions, normal, right skew, left skew. And so the assumptions I make for probability, at least, assume no distribution at all. I calculate cumulative distribution and the derivative of that to calculate estimated probability of getting a particular speed to calculate variances. But when you're looking at, say, 15th, 50th, when you pull them out randomly from a large sample, as is shown on here, and even when you divide them, like the bottom right, they're still somewhat normal. And so you can use assumptions that the covariance is going to be the normal covariance. You can reasonably assume that you can use these assumptions of normality, even though the actual percentile ranges I'm calculating don't assume that at all, because that's not normal, and a lot of it isn't. And so you have to not make that assumption in order to get more accurate results, which means if it looks like that, your 85th might have a very wide range, your 15th might be very narrow. And it just depends on every individual point. If it's a bus stop that's used all the time, it will look very different from a midsection where it's always free flow. If you look at the center of the Ross Island Bridge, it's almost a perfect normal curve because buses move very regularly. Any more questions?
I just want to ask about your methodology in finding the trouble time reliability. Yeah, I just want to check how do you...
Confidence intervals?
Yeah.
So when you're taking percentiles, there are normal assumptions that you can make in terms of confidence. P, 1 minus P, over something that I am blanking on. I apologize. But it's a way to calculate, okay, for this percentile, this is likely to be your distribution, or your standard deviation. Well, in the 80s and 90s, papers were published regarding percentile probability estimates. And so then I can use those values that I calculate based on their equations of the probability distribution function, and then using my real data, calculate a variance that then I assume to be normal for that point. And from there, I'll then use z-tables and alpha scores in order to say, well, I want the 95th percentile confidence interval. I'll use z of alpha equals 0.01.
Don't take the opportunity to ask questions and then ask have this, by the way, very interesting research. In terms of using the transit data to try to infer the traffic, right? So in most cases, I believe in most of Portland, it's probably exactly the same. We don't have, in most part, dedicated bus lanes, but we do have, I believe, signal priority for buses. How would that play out in terms of inferring the impact on the general traffic conditions?
So there are two ways that I have to address with the differences between how buses behave and how cars behave. First, buses do stop at bus stops. That's not a typical behavior for a car. And so I will then, if a bus stops, I'll then remove just those GPS coordinates immediately around that stop when I'm trying to look at traffic. Maybe I'll take one more on either side. And so if it's a very, very busy bus stop, you might remove 80–90% of buses at that point and only take the ones that pass by. For transit signal priority, it's a more complicated endeavor because you have to, A, know the actual signal timing. And that's tough because it does change throughout the day, so you might need to go in and directly do it, but it's not synced perfectly. And so if it's a few seconds off, you're going to get incorrect information. A Ph.D. student here named Wei actually did a very good analysis of integrating stop level data and signal time data for better estimations. I did not remove that. I chose not to remove that because it is extremely complicated. And just the integration is now also doing high resolution data is hard. But you can still get a reasonable idea. One interesting example of where you can see that this estimate won't work is by time of day on Powell westbound. Nope. I'll use the mouse. Right here is a bus-only lane. The bus is exiting right after it's been with traffic for a long time. It exits into a bus-only lane in order to pass through this intersection. And so congestion for this area does not represent what cars are feeling. It can't represent what cars are feeling because it's not with the cars. So this methodology really isn't that applicable in the case where buses are not with vehicles, unless you're trying to analyze the change to buses. In which case, if you had a situation where you added a bus-only lane, and you want to see, well, how'd they do before, how'd they do after? Great way to do it. But saying, how did cars do before and after when the bus has moved is not a good way of testing it. So you can't actually tell how the car did, just how the bus did. But if they're in the same lane, you can approximate the reverse.
The thing I'm curious about is there any error with like the GPS?
Yes. Yes, there is. A couple of problems. The urban canyon effect, which is buses traveling down the street, GPS is bouncing, and suddenly they're over there. You'll get lines of buses traveling through the buildings if you plot it all at the same time. It's a problem. And there is some error with that. They're pretty good about being consistently off most of the time, but they do have problems. And that's where the GIS data comes in, is I was able to take routes, and then when I knew I had just buses immediately around my route, I would then snap all points to it and assume not use GPS at all, but instead use cumulative distance along the route, which does create a certain amount of error because maybe you're a little bit behind on a curve. You might snap over here versus up. But when you're using enough data points, you can kind of get around that by assuming that most of them are going to be good. But yeah, there are problems. I mean, I literally had buses trying to drive in Hawaii. And it's just an effect of coding wrong, has a negative place in the wrong spot, or records as all 9s when it should be 1s. state plane conversions play into this, because some of the data is in Oregon State Plane North, which is a grid system that Oregon uses for a lot of what it does. It assumes feet, and everything is a perfect grid. The world is flat. It's fine. But then some of the data, like the high-resolution data, is all GPS. And so you do have to convert between, and while close, there's going to be some error.
So did you find that you were just taking out, like, sort of the outrageous values, just calling the data up, that sort of thing?
I removed buses that consistently were driving, I think, 60 feet away from where they said they were supposed to be perpendicular. Most 99.9% of buses at least recorded on the road. It might be on the wrong side of the road, but they did record close enough that you could be certain at least it's the same route. So yeah, a few buses you get rid of, but the real problem was diversion. I would say 3% of buses record as diverting at some point, either having extra points at the beginning, extra points at the end, or go a block out of their way for whatever reason. I'm estimating at 3%, but that's enough to cause problems. And so I found a way to go through and make sure that if a bus did detour, I made sure to not use the cumulative distance as calculated based on how far the bus traveled, which is included in the data, but going back again to where is it, so that it could be re-snapped to the correct point. And then that part would be removed. If you removed all buses that diverted in some way, you lost a lot of data.
So this is, of course, your part of your master's thesis. Where do you see this research go? I can see this similar approach can be applied for example, fleet data. I don't know whether Uber is willing to, for example, share their data, or for that matter, I believe there are other vendors that actually do have fleet GPS data points. What do you see this research go?
I'm hoping this research will be directly applied to research specific routes, specific segments, because it is directly applicable. For my future research, I want to expand it to include networks. I want to make sure that I could take several different bus routes, make sure that I bring in scheduling data of when they're supposed to transfer, and be able to look at how well that's working on a network level rather than just a route level. And that even though you might be able to easily take in buses traveling along the same route, making sure that you're looking at all of them is a different game. And so that is where I hope this research goes next, is to the big picture.
Question for Travis? Okay, no other questions. Before we close and thank Travis again, just a reminder that again we'll be here for the faculty and student lecture. If you're welcome, you're only welcome to join us. And for next week, we'll have Dr. Reese here to talk about effectiveness of pedestrian crossing treatment. And with that, let's thanks to Travis for great work.